I think video is not that much clear. Last past video I shared, and then I just recognize with the voice, not with the video.
I think the manual focus, you have to take away the autofocus.
Take away the autofocus. Okay.
Otherwise, it focuses on me.
I've got to remember what the name of it is.
This is the quality. You can see.
Why do people write so small?
In this part, we can understand this part is as the because we already did this, that's why we didn't that's if the voice is up, then
Now I can do it.
I should try to write bigger too.
Let's just turn off autofocus and anything else you want to do to it.
Just make sure it is visual.
what if you wrote smaller?
What if I wrote how Shajette writes?
Don't even bigger.
I mean, I can read that. I can read it.
Yeah, as far as it is focused, then it is. Just keep raising your hand or something. Give me a signal that I write it small. You have an exam on Friday? So all the homeworks are sort of already due, but it's flexible. It's only the midterm. So first question will be on quantum mechanics. We did a bit of probability probabilities in quantum mechanics. So it's mostly based on homework 6, more specifically on problem 2. But that's tentative, so don't just study homework 2. I can ask homework problem 1 also. But as of now, I think problem 2 is more probably concentrate more on it, but that's tentative. I can make it problem one. Second problem is on. Third on. Range function. Fourth on Legendre. And fifth is from I call it brain from home, if that's clear. And that's already available. So I posted it, I think, yesterday or something. Or maybe even before, I'm not sure. Yeah, I think yesterday, sorry, yeah, it's true.
I saw it on the website.
Yeah, it is there, right?
Yeah, they're posted.
It should not be too long. Especially for a break from home. I was expecting to make it longer, but it's confined to Friday, we have to bring that one. Yes, so that's better, right? Do you think it will be useful if you make this due on Monday by any chance?
Monday.
No, I'm asking you, is that, does it help by any chance so that you can study more for the exam?
Yeah.
That should be good.
Okay, so there is flexibility on that, the due date is flexible on this, but surely by Monday, right? Monday is the latest. That's it, I suppose. Oh, yeah, we have to talk about. There was a request for a review session before the midterm. Do you have any thoughts on that? There was a request for what do you call it? Review session, study session, maybe, right? Not review in the sense that I won't come prepared. You ask me questions, I can answer questions on that. I think you said it was very useful when we did this for midterm one, and it was done on a Thursday before midterm one. So,
Yeah.
and there was also a suggestion for Wednesday. So, which one suits? I am available both Wednesday and Thursday in the evenings. Zoom attendance is allowed, but my request is if it is not too much of a botheration for you, put on the camera, that helps. Yes,
I'd be able to be there either of those nights as long as it's after 7 o'clock.
so let's make it date.
I'll be fine with that.
Does anyone plan to be here?
I'll be here regardless.
Regardless, okay, so two of you.
If
Okay.
Wednesday I'll be here, Thursday I'll not be here.
Is there an advantage in making it? Is there any preference in Wednesday and Thursday between you guys? Wednesday.
Yeah.
Wednesday.
I prefer Wednesday.
Okay, so okay, so that seems like an overwhelming request for Wednesday. So Wednesday, is that 8 o'clock is convenient, right? Or could we make it 8 o'clock? It's more convenient for me to make it 8 o'clock. Okay, Wednesday.
You do here from here, yeah.
From in this room, it's not mandatory to come, especially for those who cannot reach here. Commute might be difficult at 8 o'clock. So you can attend from using Zoom, but my request is that, especially there is no one here, to have some videos on so that I can see someone. So it just helps to have some faces. Yes,
If anyone lives close enough and needs a ride, I can pick up 3 or 4 people in my car.
that's perfect. Okay, I didn't want to offer because I don't think I'm supposed to do that. So yeah, thank you, Jackson. Yeah. Okay, so coordinate between you guys if commute is a problem. And I think it is a lot more productive if everyone is here physically. So I will encourage it, but I completely understand the commute issue.
If anyone needed, then we can. Get ready.
Yeah, okay. Okay, so we agreed, right? So sorry about a
We
study session.
side and that side.
That's all right.
And if you live that side,
You can pick up that side if you leave your sides and then go side with side.
You know, on the front of the campus, there's the road that goes like past the student house and everything. I live on that, right?
Okay, because you need to go inside and you do.
Okay, yes, that's fine.
Whoever need this. 5 minutes. That's okay. Anything else in general? Anyone wants to point out? I'm afraid that this can will not last the whole thing, so I'll take 3 minutes, go and come back.
Okay.
Meanwhile, you guys chat. Yes, I'm here.
I'm still like catching up from being gone from online,
Like big.
so
I think they're
I'm
all
integrating my other classes.
I think class 5, 6, 7 is pretty.
Yeah.
I'm more. 8 and 9 is the ground that I.
Yeah.
Excited to see that wall.
I've got to catch up on that.
Like,
I'm
the
gonna-
reason we're not in this recording like right now.
Just so that we don't have all this time at the top.
Thank you. Okay. We have been doing Legendre polynomials, and in general, these are called special functions. There are other functions like Legendre polynomials. And what I want to highlight today is list a few properties, and I will do an application where you really use those features, and I'll show you how that is done. And in general, these techniques are very common in any special function. So there is always a completeness relation, orthogonality relation, and a differential equation. And any solution can be expanded in terms of that. So that's usually, and it's sort of a Fourier transform. Like Fourier transform gives you a basis. Legendre polynomials gives you a basis in another coordinate, and spherical harmonics will be the primary a set of special functions which would be useful, which we are developing at this point. So Legendre polynomials.
Yeah.
Usually any of these functions or polynomials here are defined, that you have to define them. Usually they're defined using what is called a generating function. So there is a function, you expand them, their coefficients are called these quantities. For example, this is called the generating function. Give it a name. So this is g of p comma x, but that's usually you don't write that down at all. You start from here. So this is 1 over 1 plus square minus 2 xt. So this is called the generating function, and when you expand this in a series in the variable t, that's L equal to 0, infinity. These are called the Legendre polynomials, right? That's how we have defined it. So this is Legendre. And always there will be a function that you can use to expand. And I'm thinking, what is a generating function of Fourier transform? Of Fourier eigenfunctions? Probably. Quiz. Okay. I don't have the answer immediately, but I think it should be one should have such a function. Yeah. For Fourier eigenfunctions, e raised to ikx. Okay, yeah. Okay, second is usually you say what is a differential equation satisfied by the Legendre polynomials. Or maybe I should that this alone doesn't define, right? I mean, it's good to have an explicit form for this. So P L of x, we said this is equal to 1 over L factorial, and then 2 raised to L d by dx raised to L x squared minus 1 raised to L. It's good to put this underneath this. This is what we usually do. I think that's the definition of the Legendre polynomials. What that means is that whenever you want to play around with anything, let's say you want to prove an identity associated with Legendre polynomial.
Let's see. So 0, 0, so x plus x cubed over 3 factorial.
So it's a power series expansion. So sine theta. Whenever you want to play around with it, this is a particular form you can have. That's a convenient form. There are other definitions too. For example, sine theta is equal to exponential of I theta divided by 2i. These two are related. Always, if there are two definitions, there must be a connection. This also means that if you expand this exponentials, you have to get that. That's an identity sort of. But the idea is that you can start from any of these definitions and then proceed. This is a differential form for the generating the Legendre polynomials. There are integral representations also, especially these days. What I have noticed is that this is based on personal experience, not necessarily what is advised. We have very good computers which can do good numerical calculations. If it is an integral transform, especially if it is not oscillatory, it is easy to find the area underneath the curve than sum all the series. Like if you're doing sine theta, if you have to do about a million terms you have to add, computers are good at it, but still it takes time and processor time especially. But if you can think of it as an area under a curve, sometimes it takes less processor speed. That is a personal experience I have had. But again, you have a definition and you proceed with this. This serves as a definition for Legendre polynomials. And historically speaking, for at least the first 50 or 100 years, this was the primary definitions we used. More recently, we have been using integral representations more than the series representations. So that's the generating function. That's your definition for Legendre polynomial. So next is, what is a differential equation? Satisfied by the Legendre polynomials, and it is refer. That's it. And it is also good to point out here that x is less than or equal to +1, greater than or equal to -1. And if I were to write x is equal to cosine theta, then theta is less than or equal to pi and greater than or equal to 0. So that's it. independent way of writing that. It is good to see this on the surface of a sphere. This is actually the spherical polar coordinate, the angle, polar angle associated with it with respect to the North Pole. It makes an angle of theta, and it runs, so every latitude on the surface of a sphere, if you think in terms of Earth, can be represented with a unique angle. The differential equation, we will write it both in terms of x and theta, is d by dx. There's only one variable that we are writing this. So it can be partial or total. Cos L into L plus 1 equal of 0. And if I were to write it in terms of theta, then that might be more familiar. This shows up if you were to write the Laplacian in spherical coordinates. This piece shows up. If you think of this as two pieces, so this is the same as that's your operator, and let me say minus p the sine theta, or the same thing with x. If I were to write this onto the right side, that gives you an eigenvalue equation. So an operator acts on something and it gives you an eigenvalue of L times L plus 1. So that has nice interpretations in quantum mechanics. We require that. Or in general, to solve partial differential equation, you will always convert it into a one-dimensional or one parameter equation, and that's very suitable. We can start from here and get this in your homework. I don't make it as a submission problem, but it's expected that you should be able to derive these differential equations from the definition of the Legendre problem. I'll try to do the recursive relation instead of the differential equation in the class today, or an application. So I'll decide what to do in the next few minutes. Any questions on this definition here? That's mainly I have just introduced it to you. You should be familiar with that. Okay. Third one is orthogonality. And that is dx d of x of prime x. It goes from -1 goes to +1. And this is equal to delta of L times L prime. Right? This is like two vectors coming together, a dot product if you want. If two vectors are orthogonal, it is equal to 0. Otherwise, it is 1, right? That's how we define our unit vectors. Same idea here. This is equal to 0 if they are different L. This is equal to 1 otherwise. There is a small normalization involved, and that is 2 over 2L plus 1. Whenever we want to expand a vector in terms of an eigenbasis, we also need a completeness relation. And Legendre polynomials are not complete in itself in L. It requires another variable, that is, if you're on a surface of a sphere, you really have to worry about the phi angle also. So the completeness relation will have to wait for some more time it will have, let's basically just using spherical harmonics. So port one, always there will be a completeness for a special function, completeness. And so I'll wait for spherical harmonics, right? That's the next topic we are going to. And did I cover everything? And usually there is also, yeah, that this is the important pieces. So while you're here, so this is just to get you a feel for how special functions work. Here is a quiz. So there are 4 points mentioned here. Right. Write these 4 set of so repeat above properties. For Fourier eigenfunctions. Fourier eigenfunctions, not necessarily the easiest, they are introduced to us a lot before Legendre polynomials, so you get used to it. But historically, I think Legendre polynomials came before Fourier. I think. So repeat these 4 properties for the Fourier. And Fourier eigenfunctions has a completeness relation associated with it. So have that. Okay, so based on this, there is at least for Legendre polynomial, we have this can be used to repeat your L. There is also a recursion relation. So this is a 5th property, but not necessarily recursion. Spelling of recursion. Is that right?
Yeah.
Recursion relation. It basically tells you that if you know L and L minus 1, then you can calculate L plus 1 and if I can find it. Notice again, if you know L minus 1 and L minus 2, you can calculate the L. So if you know 2 of them, then you can get the next one. So that's very useful to calculate the recursion relation. Is that clear how that works? Have you come across recursion relations before? Or should I?
A while back, but then.
Okay, so let's just do a few, like this is in your homework also. So I'll take you have to start from 2 because 1 and 2 1 and 0 has to be known, right? So let's say if you have L equal to 2, substitute L equal to 2, so that's 2 times the 2x. This is equal to 2 times 2, 4 minus 1, that's 3 times x. The L minus 1 is 1 and minus 2 minus 1, 1, so that's the 0 of x. So I immediately have the 2 of x is equal to 3 by 2 x times p1 of x minus p0 of x. We know it is necessary that we know the 1 and 2, the before, I mean, if you're starting with 2, at least 2 you have to know. This comes out to be equal to 1 and p1 of x is x itself. So that's Oh, what happened?
So there
Oh.
is 1/2 PC.
Thank you. So that's what I was missing. Thank you very much. So that's put in the x here, so that's 3/2 x squared minus 1/2, and that's indeed correct. We know that P2 of x is, so that's how you do this. So I can give you P100, and if you know 99 and 98, it generates the next one. So if you know 0 and 1, you could get 2. The polynomial of degree 2. If you know 98 and 97, you can calculate 99. So you recursively keep producing the next ones. Let me show you how this can be used in a physical problem instead of proving these identities. Most of the time, you're, at least as you proceed, you will assume that all this is correct, and you'll be more of a user of this rather than proving them. But at the same time, manipulating these expressions also has techniques involved, which is useful, which I will encourage you to look into. The homework is the best place to look for these things. Some of them are optional notice. That just means that you don't have to push yourself into submitting it, but it's very necessary for learning the whole topic. Is that clear? I don't ask you to submit it, but it's expected that you know it. It's like a textbook, like that's what we refer. Okay, so as an application, and we start from here and I'll go on that side. So let's say, what's the electric potential due to a charge density? Electrostatic electric potential given a charge density. Is that a familiar? Is the question clear? So maybe very quickly write down your equations minus that's your Maxwell's equation, right? Charge density, and it also tells that the cross of the electric field is equal to, Maxwell equation tells cross of the electric field is equal to what?
Minus change in magnetic field.
Very cool. Rate of change of magnetic field, good, but we are saying it's static. The moment you write the second equation, which is true only for statics, this implies that the electric field is equal to negative gradient of phi, right? That's the existence of energy. Force is equal to negative gradient of energy. This is electric field can be written in terms of a potential. Is this always true? Is there a modification in this equation? Ever? Right, that's a voltage. Electric field is the negative gradient of the voltage, or voltage is the integral of electric field. Is that always true?
It's like a gauge.
You're thinking correct, but electric field doesn't depend on gauge. It's the potentials that depend on the gauge. Like it's like saying change in energy, right? Energy has an origin, like gravitational potential energy is always with respect, or if it is on the surface of Earth, we say this is 0. So that's sort of a gauge. You're setting your origin, and the change in energy doesn't depend on it. So electric field usually doesn't depend on gauge. It is the potential that depends on the gauge. But electric field depends on something else. Like I said, this is 0, right? This is statics. If it is not static, what is the electric field?
The negative, the rate of change of the magnetic.
Very good. So maybe I didn't finish the question precisely. That's why the answer is not that. This is more precise nature of the electric field. Electric field is not the negative gradient of the potential all the time. If that is magnetic field, or if it is not static, this is what term contributes. But you're talking in terms of statics, then that term doesn't exist. Put this in the first equation, and you immediately have del square epsilon naught phi is equal. Oh, I messed up, right? There's a mistake in this. That was my question. There's a mistake in this. Very fundamentally bad mistake. In the three equations that or third equation I'm just writing. First equation has a mistake.
Is it the minus?
Yeah, there's no minus sign, right?
Okay, I was wondering why you put.
Yeah, there's no minus sign. My bad. Okay,
There.
so Maxwell equation is just the divergence of the electric field is equal to charge density. And this means that you can get the electric potential using the charge density. And once you have the electric potential, derivatives are usually very easy to do, always doable. Integrals are not always doable. So if you write this expression, once you get the electric potential, you're guaranteed to be able to find a electric field. So usually the idea is to solve for this equation. So again, electrostatics, what do? Give me the charge density, any charge density. This equation will give you the solution for the electric potential, right? There's a general feature involved. Usually it has integrals, so it's not very convenient. Most of the time integrals are not doable. These days we have computers, so numerically they're always doable as far as they're finite. If there is no infinities involved in it, then integrals are very nicely done on a computer. If there's an infinity, then usually there is a struggle with it. So the electric potential of R in terms of the charge density, this is equal to 1 over 4 pi epsilon naught, and you integrate over all the places where there is a charge density. That's your Green's function if you want, whatever is the 1 over r minus r prime, that's your Green's function. And remember, this is how we motivated the Legendre polynomials. 1 over r minus r prime, it is nothing but this expression here, right? If I were to write r and r prime square, this is r square, this is r prime square, and this is 2r dotted with r prime. So this is r minus r prime square. That's a scalar associated with it. So we immediately know that that's where the origin of the Legendre polynomials is. So let's do a simple scenario where you can evaluate the charge electric potential for a given charge density. Let's put it on a surface of a sphere. So charge density for which is the charges are only on the surface of a sphere, like think of it as a conductor, and then it will be there is a sigma, but first of all there is r minus a. So this exists only on the surface of the sphere of radius r. Is that clear? Charge density exists only on the surface of a sphere of radius r. I'm providing that. And next, I have to provide what is the angular dependence on it, on a sphere. If I have to define a function, it depends on theta and phi. So let me say the theta is PL. Let's say PL cosine theta. And that's still, this is dimensionless usually. PL is dimensionless. This is a 1 over length involved. So I have to provide a charge density. So let me say that's sigma, that's a constant. So that's charge density. That's not uniform though. Or better, let me write it in this form. So this times sigma theta phi, that's the charge density, right? Sigma theta phi is equal to charge per unit area. Clearly not uniform, where you're on the surface of a sphere matter. And let us ask the special case that this is equal to some constant sigma times PL cosine theta. It has no phi dependence in it, the way I have written it, so it has no phi dependence. I have to provide which Legendre polynomial it is. So for example, if I say L is equal to 0, let's go back here. What is the distribution for L equal to 0? Can you
Uniform.
a uniform charge density? Very good, because P of 0 of x is a constant, right? So that's 1. So that means that's just a constant. So, and the next question comes, what is it for L equal to 1?
It's on theta, so
L is equal to 0, sigma theta phi is equal to sigma times P0 of cosine theta, that's simply sigma. Right? And which is constant, uniform charge density. For L equal to 1, this is sigma theta phi is equal to sigma times P1, which is just cosine theta. And how will this look like? If theta was equal to 0, so notice this is a sphere, and let's say that's your z axis. Theta equal to 0 is right here, cosine of 0 is 1.
so is it like polar?
Polar, exactly. So here it will be +1, there is a lot of charge. So this is +1. And when theta is equal to pi, it is -1, so it is negatively charged here. And if I were to use how far I'm going from the what do you call it? Away from the radius as a measure of the function itself, it's called polar plot, right? Polar plot. Then this would be cosine theta, correct? At theta equal to 0, so this will be like this. At theta equal to 0, it is like this. Is that clear? Because this has to be 0 here. Maximum is 1. This side is negative. Overall, if you are to physically see it, the best is there is a lot of charge here, positive, positive, positive. Then there is less charge here. So this is positive still, less density, less, and then it becomes negative. So this is 0 here, neutral, and then becomes more, and more, and spherically do that. So a maximum positive charge, maximum negative charge, and then it goes into 0. That is how it will look like. So that's your cosine theta. L equal to 2. Sigma theta phi is equal to sigma. L equal to 2, we said, is 3/2. Cosine square theta minus 1/2. The main idea here is that this is oscillating once. Remember your PL of x. So this is PL of x, and x goes from 0 to -1 to +1. L equal to 0 is a constant, right? That's L equal to 0. L equal to 1 goes from -1 to +1, and it linearly goes in there. That's going from -1 to +1. And the second one starts from or P2 starts from a positive value, goes down to half, and then comes back. Right? So the same thing, you have to do it here. It will be positive on the top, positive at the bottom, and somewhere in between, it will go to a negative and then come back. So it goes to 0 twice. So these features can be used to have a charge density, which are fundamental in the sense that any charge density which depends on theta can be expanded in terms of the L theta, which is what is called multipole expansion. Like in electrostatics, you call this multipole expansion. Here, we're just saying that any function can be expanded. But let's see what is it for. So let's fix L equal to 1. Let L be equal to 1. So for our purposes, let it be just cosine theta, and let us try to find the electric potential. So phi of R theta phi is equal to, so that's your R observation point, and that's equal to 1 over 4 pi epsilon naught, and we have sigma also, right? So that's sigma, and we have to integrate over the R square dr d theta, and this is R prime, right? R prime sin theta prime and d phi prime. Phi 0 to infinity, and what we have is sigma, which is sigma itself.
But we already took sigma out.
Oh, but sigma as well, thank you. And PL cosine theta for L equal to 1 is cosine theta, but cosine theta prime divided out by R minus R prime, which is R square plus R prime square minus 2 R prime times cosine of gamma. Notice it's not cosine of theta, this is cosine of let me explicitly write this. So this is equal to
Cosine bar dot.
cosine theta prime plus sine theta prime and cosine of phi minus phi prime. So not a simple expression, that's an explicit way to do that. We can always, not necessarily everywhere, at least in this problem, we can decide to choose our observation point to be fixed on the z-axis. There is a significant simplification in that. But using Legendre polynomials, you can actually avoid that completely. But let's do the simple case where we choose theta equal to 0, and after that phi doesn't matter, right? Once you choose theta equal to 0, phi doesn't matter, and that's equal to R0, so it's equal to sigma over 4 pi epsilon naught. And oh, what did I miss here? I missed something in this. When I was writing the sigma, sorry, the charge density, notice I had a delta function in it, right? So that's a delta function also. That's useful to do that. And this is R prime, right? We are integrating on the charge density. The delta function immediately allows me to calculate the R integral. So replace all the R primes with A, and that's A square sigma A square, and I have 0 to pi theta prime sine theta prime 0 to pi d phi prime cosine theta prime, and R primes get replaced with A, R square plus A square, and now we are setting theta equal to 0. This goes away. So that's the advantage of choosing on the z-axis. This immediately goes to 0. Cosine of theta is cosine of 0 is 1. So this is minus 2 R A cosine theta prime. And remember, that's here the generating function for the Legendre polynomials. There is no phi prime integral, so complete that also. Well, to sigma 2 pi a square over 4 pi epsilon naught. You have 0 to pi theta prime sine theta prime. That's the Jacobian coming or the scale for the area itself, so it's better not to touch that. Don't mix it up. Sine theta prime divided by square plus a square minus 2. Maybe pull out a r a over r also, but let's see what can be done. We have our definitions for the Legendre polynomials in terms of x cosine theta prime. So let's introduce t because x could be confusing. So let's like until now, this was just construction of the problem. Laplacian immediately tells us what is the electric potential. I chose a charge density and did the elementary integrals, or this is just a construction itself immediately tells me that I have to integrate over the surface. So this is the integration over the surface of a sphere. But now replace everything with t. So let's say t is equal to cosine theta prime. And this is like x that we have, since x is a coordinate in space. Let's use t. Or should I? No, let's not use t, right? Because when we define the Legendre polynomials, t was used for r over r prime. Let's say x itself, or mu, right? Yeah, that's what Maxwell used. So Maxwell used mu is equal to cosine theta prime. So d mu is equal to derivative of cosine is minus sine theta prime d theta prime. When theta prime is equal to 0, mu is equal to +1, and when theta prime is equal to pi, right? That's the maximum value you can take. Mu is equal to -1. So our integral, of course, that is 0 equal sigma 2 pi square over 4 pi. When it is theta prime is 0, this is +1. This is -1. D theta sine theta is minus d mu. And cosine theta prime is PL of mu, right? So it is P1. So this is 1. P1 of mu divided by, let me yeah, let's just write it as r square plus a square minus 2ar mu. Maybe define t as r maximum of no, I think t as less over r greater, where r less is minimum of r and a, and maximum of r and a. So whatever is the bigger quantity that comes out is 1 over r greater. And use the negative sign to flip the sign of the integral. -1 to plus 1 p mu p1 of mu divided by, if I'm taking greater, so this is 1 plus p squared minus 2 p mu. Great. Any questions until now? Notice I have not done any integral yet. And I won't do an integral at all. That's where the so I kept this on. We will use orthogonality property of like the polynomial. Now this has the generating function showing up. Write this in terms of Legendre polynomials. So that's a square 4 pi epsilon naught 1 over r greater minus 1 plus 1 d mu d1 mu, and this has the definition in terms of a series that this is L going from 0 to infinity p raised to L and PL of mu. It's all symbolic. Notice I've not done anything. I'm just manipulating the whatever is available to me. And the manipulation here is going to be there is an integral of a sum. I'll change the order of this. First do the integral and then do the sum. This is equal sigma 3 pi square 1 over greater. Bring in the sum in here. Sum in the front, that will be equal to 0 to infinity. P can come out of this integral, so that's p raised to L. And the integral is minus 1 plus 1 p mu p1 of mu p L of mu. What is that integral equal to?
Delta of 1 and L.
Very good, right? So that's delta of here, one of them is 1. So out of all the sums, only one contributes. That's what it means. This is a dipole. So the cosine theta here is a dipole. So only one term in that whole expansion contributes. That's the physical significance. But let's do that. So this is equal to 2 times. So this is equal. What is that? Not done. I'm just symbolically working. Not done real integrals at all. I'm using orthogonality. It's a projection in a function space. It's divided by 4 pi epsilon naught 1 over r greater. This is summation L equal to 0 to infinity p raised to L. This is delta of 1 and L. Only when L is equal to 1 it contributes. In this whole sum, only the L equal to 1 term contributes. L equal to 1 term here is called the dipole. If L is equal to 2, it will be called a quadrupole. L equal to n, it will be the nth pole. Right? That's the definition of a multipole. And there's also this normalization 2 over 2 times 1 plus 1, so it's 2 by 3. So it is 2 times 1 plus 1. So that's 2 by 3 basically. Right, that's coming from this piece. Any questions on how that's going? That sum contributes only when L is equal to 1. So what complete that. So electric potential at on the z axis, that's some we still had a constraint there, but that also can be released very easily. So let's equal to sigma 2 pi is square over 4 pi epsilon naught, 1 over r greater. And this whole thing survives only when delta is L is equal to 1. So put that in there. So it is t raised to 1. The L is getting replaced with 1 and 2 by 3. And t, remember, now replace your r less over r greater. Right? So this is equal to sigma times 2 pi a square. Oops. 4 pi epsilon naught 2 by 3, 1 over r greater and r less over r greater. There are two situations: what happens inside the sphere, what happens outside the sphere. So this is equal to sigma times 2 pi a square over 4 pi, actually 4 pi a square, right? So that's the area of the sphere. 4 pi a square times 4 pi epsilon naught is the units itself coming in, and it's 1/3 of if r is less than a, so this is inside. So if r is less, so this is r less this r, right? So greater is a, so it's r over a square, right? If r is less than a, and let me just say here, and it is 1/3 of a over r square if a was less than r. And if you notice, that's actually, oh, did I miss something? No, right? I think it's okay. Yeah. I didn't miss something. Where is my cosine theta? Isn't this a dipole field? A, Z. Did I mess up? One.
Your cosine theta is absorbed by the p sub 1 of mu.
Oh, no, I think it's okay because it's on the z-axis. So on the z-axis, if I were to release this, then this will have a theta in there, right? It will be cosine. So in general, so this is not just r, this is on the z-axis, right? So r is on the z-axis, So this is on z-axis. If you were to release that feature, then there is a cosine theta. That's why I was confused. This is okay. And that 1/3 is coming from that feature. But again, I want to emphasize that's a technique here. You do nothing, right? You have not done any integral at all. There is no tricks used. You expand. It's like a expand the vector using an expansion, manipulate it, and then use orthogonality to solve. So that's usually standard in a function space. I'll stop here. I can do the recursion relation, but I don't think it will get over in 10 minutes. So, okay. Do that for p equal to 2, for example, L equal to 2. So those are the things I can ask in the exam. But that's too much for to ask in an exam. Info still
Uh,
clear.
it's really bad.